Lord Jesus, we thank you for this afternoon. We thank you for the session that we are going to have. We thank you for your ever so great, and we thank you for we are going to share the topic on waves. I pray that may you send your Holy Spirit to guide us as we listen to and as we share what we are going to share. In this session, Father, may you enable the learners to understand the concepts, and may you enable me to give what is understandable to each and every one. At the end of the day, we shall live with something that we have understood. In Jesus' name I pray. Amen. Okay, so ladies and gentlemen, good afternoon. Since you are not able to talk, I'll be checking on the chat. Okay. So we are going through waves, and we're going to look at basically the introduction today, because it is a common topic to each and every one. It is something that we need to maximize. I hope I'm clear on that. We shall be joined by some other person just in case. Just in case I stop somewhere, there's another teacher who will be joining us. However, in case of anything, feel free to add, supplement, ask a question, or because this is familiar content that we've been used to. So, waves. Okay. You know that waves is simply a disturbance of a medium. And waves that we talk about in physics, if I'm to write something, if this is a wave, for example, we always say that particles are being disturbed from their resting position. The rest or equilibrium position is the line, this horizontal line, we call it the rest or equilibrium position. Now, the shape of the wave is one that is described by the particles being displaced from this equilibrium position. So, particles displaced take a shape, like I can show you. Particles being displaced are either displaced upwards or downwards. So it is the shape which, after joining the displacement of the particle points, they form a kind of a wave that we talk about. Otherwise, it is not simply a line, or it's not simply a curve, but this is a shape of the particles that are displaced from the equilibrium position as a wave is progressing from one point or from one position to another. Is that okay? So our definition is very simple. It's any disturbance from an equilibrium position that travels from one region to another. And then we are saying that the wave motion is simply the transfer of energy. So as a wave is progressing from one point to another, there is energy carried with it from one point to another. So we are saying that waves are classified into two. We have the electromagnetic waves and mechanical waves. These are classifications, not types of waves. They are just a classification of waves, where electromagnetic waves are okay. So we've talked about electromagnetic waves and mechanical waves. So let us look at mechanical waves. So when we look at mechanical waves as a classification of waves, these are waves that are produced by disturbances of a material medium. So take note of the word material. Take note of the word material medium. So material medium, and they are transmitted by the particles from the medium oscillating to and flow. Is that okay? So mechanical waves in this case require a material medium. What does that mean? That waves like sound waves, water waves, these can't propagate, or these can't be transferred from one point to another without being carried by a certain medium. I think a famous example of these kind of waves are the sound waves. Are we together? Any questions so far? I can check in the chat if there is any question, so that we don't miss out on anything. We are going to go through roughly because we are revising, but this is another important section. Okay, if there is no question, we can continue. So we are saying that mechanical waves are those waves that require material medium for their propagation. Is that okay? That require material medium for their propagation. And we are saying examples include the sound waves and water waves. So, like I told you at the beginning, I'll be stepping out a bit, but there is one teacher who is with us. Mr. Pio will be taking over from here, but I'll be coming in here and there. But otherwise, we still continue with mechanical waves. We've done mechanical waves. Now he's going to take us through electromagnetic waves. Is that okay? Okay, as he's joining, let me take us through the electromagnetic waves. And we are saying that these are waves produced by disturbances of varying electric and magnetic field. Note the word varying electric and magnetic field. So what is the basic definition of mechanical wave? So, okay, let's first go back to mechanical waves. We are saying that these are waves that are produced by the disturbances of a material medium and are transmitted by the particles of the medium oscillating to and flow. That stops there. So this one is the second part is just a characteristic of a mechanical wave, that it requires a material medium for their transmission. Is that okay? They require material medium for their transmission, but the definition is the one given before. Is that okay? Someone who asked for the definition of mechanical waves. The key points to note are it requires material medium, and also particles of the medium oscillate to and flow. Is that okay? Okay, good. So that is mechanical waves. You remember these are not types, they're just a classification of waves, mechanical and also electromagnetic waves. Okay, we go to electromagnetic waves. Teacher is going to join us so shortly. Electromagnetic waves, these are waves produced, I talked about it, disturbances of varying electric and magnetic field. Varying electric and magnetic field. The varying electric and magnetic waves. So we are normally used to electromagnetic waves, which you will know that the examples of electromagnetic waves include all the electromagnetic spectrum. You know them, like we shall be guided. Okay, I beg to stop here for now. Then Mr. Pio will take us through the next session. Yes, Mr. Pio, you may unmute. Mm. Mm.
I can't keep waiting, Mom. I don't know whether to come or not.
Okay. Hello, Mr. Pio. Are you sharing?
Yes, I'm getting.
Okay.
Yes.
Okay. I about or I can continue sharing as you are looking for it. Maybe you can save it on the desktop.
Yes, I will share. I will send you the message when I share.
Okay.
Yes.
Okay. Yes, ladies and gentlemen, as he's looking for it, let me continue. Sorry for that. Okay. We are still looking at okay. I hope you can see my screen again. Can you?
Yes.
Are you able to see my screen?
Yes.
Okay. You are able to see that I'm displaying electromagnetic waves.
Yes.
Okay, let us continue. Oh, so electromagnetic waves examples. Example, we said they include all the electromagnetic spectrum, and that is the X, the infrared radiation, the ultraviolet, the radio waves, the TV waves, microwaves, all those radiations that lie under the electromagnetic spectrum. So they qualify to be called electromagnetic waves. We said these waves are characterized by both electric and magnetic field. That's why they are called electromagnetic waves. So we mentioned that examples include the light waves, the gamma rays, the radio waves, and all the electromagnetic band waves. Yes, a question? Yes, please, Yiga. Yiga, you have a question? Okay. So we can continue. The properties of electromagnetic waves. We said before we look at the properties, we have a note that electromagnetic waves all travel at the speed of light, which is 3 exponent 8 meters per second. So when you talk about the 7, yes, please, Yiga and Stena. Maybe you are writing in a chat, let me check. I can't unmute, but the screen is showing. Oh, now me I'm for longitudinal waves. Okay, let me check again. It should be this one. Are you able to see this screen? Properties of electromagnetic waves. Okay, thank you so much. So we are saying that electromagnetic waves are, we said, are waves that are characterized by the electric and magnetic fields and their properties. The note first is that they all travel at the speed of light. The speed of light is 3 exponent 8 meters per second. So here we give the properties of this kind of waves. They can travel in vacuum and therefore do not require a material medium for their transmission. So you remember what we talked about concerning mechanical waves? For them, they require a material medium. So we are saying that electromagnetic waves travel at the speed of light. There is a typing error here because the speed of light is supposed to be Mr. P, are you ready?
I'm trying to share it.
Okay, should I stop?
Yeah. You first share yours. And you allow me on that name showing of your Livingstone.
Not there, right?
Because I've tried this one for them, it's not accepting. But now I'm joining with this one that shows of your Livingstone. They allow me to unmute on that. I can easily share on this one.
To allow you to enter.
Using this one for your Livingstone.
Okay. Okay, friends, as he's winding up, I think I can continue sharing our. Okay, so we are here. And we are saying that these are the properties. These are the properties of electromagnetic waves. I was saying that there was an error here on okay, Mr. P, you are sharing?
Yes. Can I share?
You have shared, yeah?
Yes.
Okay.
So can I continue from there?
Yes, don't forget to correct that mistake. 3 times 10 power theory. The electromagnetic waves travel at a speed of light, which is 3 times 10 power 8.
Yes. Thank you so much, Mr. John.
Okay.
Good afternoon, members. As Mr. Jonas as we have been discussing the properties of electromagnetic waves, like in this point when we are giving these properties, we have said that electromagnetic waves travel at a speed of light, which is 3 exponent 8 meters per second. That 3, we shall just correct it. It is supposed to be, you correct it, it is supposed to be 3 exponent 8, not 3 that we have at that point. So that is the speed the electromagnetic waves move when they are traveling. They travel at that speed. So when we talk about, the variation of those things, you find that electromagnetic waves, they are made up of varying electric and magnetic vibration. As you know from the definition, when we looked at behind here from the definition of electromagnetic waves, we said that these are waves produced by the disturbances of varying electric and magnetic field. So that property is just picked from the definition as earlier being explained by Mr. John. Then finally, when you look at this one, we say that they vibrate with a higher frequency. When you look at the vibration of the electromagnetic wave, their frequency is very high when they are vibrating. They have a higher frequency during their vibration. Then we have this one of they have no charge. Surely when you look at the electromagnetic waves, for them they don't contain any charge. So when we ask you to state or to give the properties of electromagnetic waves, we basically look at these properties that we are having from here. These are the properties that we give when we are to give the properties of electromagnetic waves. So before we go to electromagnetic spectrum, if you have a question, you can ask if you have any question concerning them. Some are saying I increase on the screen. Let me increase on them. Sorry. Let me just turn on this phone as I increase on the screen because this one I'm using the phone for sharing. So let me just put it, then we change it. It can increase. I hope they are now clear from there. Is it okay now from there? You will just send me a message and tell me that now they are large at that point. Okay, that's good now. It is okay now. So let us look at, if there is no question, let us look at someone is asking that, can he talk about the wavelengths when we are talking about the properties of the, like in part of way, like giving properties of electromagnetic waves. Now, on the side of the wavelengths, like when we come back here, on these electromagnetic waves, remember we had mechanical waves and electromagnetic waves. And when you look at the examples of the electromagnetic waves, we had these light waves and the gamma rays. This is what we had as the examples on these things. So when you say you want to talk about the wavelengths, you basically write all your point and I see how your point is. We first see at that point. Because when you just say about that, maybe you want to say that electromagnetic waves, I don't know what you want to talk about in the wavelengths, but maybe your point is not all clear. I wanted you to first explain that okay, he's talking about that they have short wavelengths. For that one of having a short wavelength, yes, electromagnetic waves, they have a short wavelength. From there, you can write it if you see that you've exhausted all these properties and you want to add more, you can include it also. It is a right point. It works also at that point. You can just talk about it. Now, we go to this part of electromagnetic spectrum. Now, in this electromagnetic spectrum, it is now divided into, as you look at that spectrum from this color that we have from this side up to the last color. Now, that color is divided into several types of, now like just classes that we have at that point, where at the whole of it is containing the visible light. Now, that visible light that we are having at this point, this is where you will find all the rays that we normally talk about, where we talk about the gamma rays, the X-rays, then the ultraviolet light, then we talk about the infrared rays, then we have the radio waves, whereby the radio waves, those waves we, like when we look at the signals, like when you're looking at the radio, we normally have the signals for the radio, where you have the FM, we have the TVs, we have AM, in those things. So electromagnetic spectrum is consisting of those classes of waves that we look at. You find that at first the gamma rays, there is no way I can illustrate it from here. On this thing does not illustrate. I wanted to illustrate how these waves move. Like on this gamma rays, when the gamma rays are just starting, you find that for them, the waves are too close to each other. Those are the gamma rays that are starting at that point. But when we are continuing to go to the X-rays, that's why when we are continuing to go to the X-rays, at that point, you find the wavelength starting is increasing slowly. The wavelength is trying to increase as you're looking at those wavelengths that we have at this point. For the gamma rays, it is at 0. When you look at it, it has 0.000 nanometer. When you go to the X-rays, you see the distance that we have, the wavelengths that we have at that point. You go to the ultraviolet light, you see it is distance also. So that is the way the wave runs. For example, in case you're told to draw electromagnetic spectrum, look at the way the waves are running. You might not be in position to, like this thing is drawn that rectangular thing is drawn and we have placed them in two colors. But for you, when you're drawing, you can just draw a rectangular thing. Then you start just like the first one, you're going to make the lines to be near each other. As you're going to the X-rays, at least you reduce now the distance, you try to adjust the distance slowly. When you go to the ultraviolet light, the distance keeps on increasing slowly, not until you reach the radio waves where the distance is going to become too large. That's the way you can draw, and you name them that the gamma rays, the X-rays, the ultraviolet light, each space you name what it represents at that point. That's the way you can name the electromagnetic spectrum in case you're being asked to draw it, because they can ask you to just draw it. So in case you have any question about it, before we go to the differences between electromagnetic waves and the mechanical waves, you share it on the screen. You can just write a message and you ask it from there. If there is no question, we look at the differences between the mechanical waves and electromagnetic waves, where as you know the definition of electromagnetic waves, like when you're giving the differences between mechanical and electromagnetic waves, we normally find candidates writing, for example, like the first difference, we are saying that electromagnetic waves do not require material media to travel through, which means for mechanical waves require material medium to travel through. But when you're writing them, we encourage candidates to write it complete all by saying mechanical waves require material medium to travel through. Because we normally find people, when they are writing, they say this one requires this, while this one does not require this, just putting it in just short forms like that, which cannot properly make you to earn marks. You just need to complete all of them. That one, we looked at it when we are defining. Someone is saying, why is one? Someone is asking, let me look at the message someone sent from here. I'm trying to look at the message because I saw it on the screen, but I didn't see it. Let me first see it very well as we are going to look before we go to the difference. Someone is saying that someone is saying that why is someone wants to know, the question keeps on jumping, sorry. Someone wants to know what causes that one end is blue and the other end is red, that what causes that. Then another one wants to know, so when you look at those things, I told you that when you're looking at it just blue and the red, we are not using it that is the color we are supposed to use in that thing. But I told you that we have just used those colors as you roll when you're writing soft copy notes, just in order to make you to know that this part, when you look at this part, which is having like, that color is gray. That part is just that it represents the gamma rays. Then when you go to that blue one, that it represents the X-rays, but doesn't mean that those are the colors you're supposed to write there. But for you, when you're writing it, if you're to draw it in your paper, I told you that when you're starting, you just start drawing your lines slowly, slowly. Like when you're starting, you make the lines to be near each other, is what you're supposed to make when you're representing the gamma rays. Then when you're going to represent the X-rays, at least now you adjust the lines to be spaced now at that point. That's what you're supposed to represent, but that doesn't mean that we are going to put those colors. That is what we are supposed to use in it. So when I see someone raising up the hand, let me allow you and you ask. The host is supposed to allow you to ask. I'm not permitted to allow you to unmute you. So I don't know whether Mr. John can do it such that you can ask your question and we listen to you. Let Mr. John help us. Then you ask, but if you see, you can just type it and you just send it via message and we look at it. So we were still talking about the difference between mechanical and electromagnetic waves. Now, for electromagnetic waves, we have said that they are composed of vibration, while mechanical waves are only composed of electric and magnetic fields. So you find that for electromagnetic waves, as you know, the electromagnetic waves, they deal much of vibration. You find that there's a lot of vibration. So for them, they are composed of vibration. But for mechanical waves, they are composed of electric and magnetic field. For them, they have the fields in them. Then, since electromagnetic waves do not require material medium to travel through, which means they cannot travel through a vacuum, while the other can travel through a vacuum, like while mechanical waves travel through a vacuum, since for it requires a material medium to travel through. Those are the differences in case you're being asked to give the differences. Now, you want the other ones, we have been talking about the classes of waves. I want to look at just the types of waves now. You don't confuse the classes with the types. Now, for types of waves, there are two types of waves. The wave motion. We have the transverse waves and the longitudinal waves. Those are the types that we have for waves, where the way of illustrating, I told you that this gadget I'm using cannot illustrate them. I would be in a position to illustrate for you. On the types of waves, we find that, like when we start with the transverse waves, you find that these waves, their displacement, the way particles are displaced in the medium, for them they are perpendicular to the direction of the travel of the wave travel, or the travel of the wave. When those particles are being displaced, the way they are displaced, they are ever perpendicular to the direction of the travel of the wave. That is the definition that we can give for the transverse waves. Now, when we look at like the characteristics of the transverse waves, in case you're being asked, because for them they consist of the crests and troughs. As like when you're drawing, like when we were starting, Mr. John had illustrated a wave where it drew, we had the wave particles, where, like when you're starting from the definition of the wave, it is consisting where we normally have the amplitude, we have the wavelengths. There is a part which is being represented by the crest, and there is a part which is being represented by the trough at that point. So we find that the like if you're giving the characteristics of the transverse waves, we say that the transverse waves are characterized by crest and troughs, where a crest is the part of the wave above the line of a zero disturbance. So like when you have a zero disturbance and we want to define a, you find that a crest is above there, there is no way you can illustrate it on this gadget that I'm using. Does not illustrate, but I will be able to illustrate for you. I don't know whether you are understanding. So you find that the crest is a part of the wave above the line of a zero disturbance, but the trough is a part of the wave below the line of a zero disturbance. So a trough is downwards, where the crest is that upward displacement is what we call the crest. So the trough is that downward displacement that we normally have from down. That is what we have in that. Now, we want to look at the examples now of transverse waves. Mostly for transverse waves, like we know the particles are displaying and they are perpendicular. You find that water wave is an example of the transverse wave. We give the light waves, then the waves due to the plucked strings. Those are the examples we have. And all electromagnetic waves, like we gave the example of electromagnetic waves. So when you put all the electromagnetic waves, as we said, the sound waves, we have the gamma rays, we have the X-rays, all those ones are example of the transverse waves that we give at that point. Now, when we look at longitudinal waves, for longitudinal waves, those are waves in which the displacement of the particle is parallel to the direction of the travel of the wave. So for them is when the particle is displaced, like when the displacement of the particle, for them you find that they are parallel to the direction of the travel of the wave. So for all of them, they are going to the same direction. That's why you find them that they are all parallel in that point. You differentiate between the transverse and the longitudinal wave. Now, when we look at it, like here, for it, this consists of the area function and the compression. You look at that, how the area function looks like and how compression looks like from the word compressed, so that they are near each other. That's why we have the compression in that thing. The same, like down here, those arrows just show the direction of the travel of the wave. That is the way they looks like. For it is consists of the area function and the compression, while the transverse was consists of the crest and the trough. Now we look at the characteristics of the compression and the area functions. Now, for compressions, these are regions of higher particle density in a wave. But rare functions, if they ask you to define them, rare functions are regions of low particle density in the wave, as we looked at. For them, the compression, those lines were near each other, which means they have the higher particle density in the wave. But the rare function, since they were spaced, they have the low particle density in the wave. So you give them, if you're being asked to define them, those are the definitions we give you. Now the examples of longitudinal waves, we have the sound waves. Like as you see the sound waves, whenever the wind is passing, you'll be hearing those waves from there, or waves on a compressed spring. Those are all examples of the longitudinal wave that we give. If you're being asked, you can just give those ones. Then we look at the differences between the transverse and the longitudinal waves. Now, if they ask you for the difference between the transverse and longitudinal wave, I normally tell candidates that the first difference is it comes from the definition of the two. You pick the difference from the definition. For transverse waves, the particles move perpendicular to the direction of the wave travel, while in longitudinal waves, the particle move parallel to the direction of the wave or where the wave travels. That is where we can have. Then if you want to give another definition, you look at this one, they are given only one, but you can go to that one. We said that for transverse waves, it consists of crest and draft, while the other one consists of the rare function and the compression. You can talk about that. And so many, like you're given them as you were given, you can talk about all of them as the differences. Someone is saying that, can it also be tabulated? I don't understand what, are you meaning that tabulating them in the table? If it is to tabulate in the table, you can write all your question in full, I see it. But you can write it in a table form, it's okay. Now at that point, it is okay, you write it, you can even write it in the table form. Now, we want to look at the representation of the wave, how a wave is represented, and that is where we get the definition of those things. Like the way that line is moving, that is the way the way the wave is represented. Now you find that in this wave, where we are representing, that distance from down from the initial position, equilibrium position, going to that peak where you're seeing the peak, that's where we have the amplitude. Then the difference between one crest to another, which means those ones we call the crest, one peak to another, that's where we have the wavelengths. Even down, even though I'm using the drop down, that's where I have the wavelengths also from there. So like you can be able to ask to define them. Then when you look at this one, the displacement again is time graph. Displacement again is the time graph where we have displacement versus time. So now you find that from this axis of the displacement up to where that dotted line is, where we have this graph is ending, is where we have the period. Then the upper side, we have the crest from there. So then down there we have the amplitude. So that is the displacement. Again, is the time graph that we have at that point. So now you can be asked to define what an amplitude is. Now, when you look at this thing, you look at where we located an amplitude, you find that an amplitude is, you see that we call it that green line, that arrow, green arrow where we have the amplitude, where we say now you can define amplitude according to that green line as the maximum displacement of a particle from its equilibrium position. As you see from this green line, this is where we have the maximum displacement of the particle from its equilibrium position. Is where you can get the definition of the amplitude. Then the wavelengths, you saw that the wavelengths is between one crest to another or one trough to another, as we saw. That's why I say that is the distance between two successive particles in a phase. That is general, but they can tell you that define the wavelengths as applied in transverse waves. So if we are talking about them, we can say the distance between two successive crests or successive drafts. if we are to talk about the transverse waves, if you are defining it. But if a general definition, if someone just wants you to define a wavelength in general, we say a distance between two successive particles in a phase. But if as applied in transverse waves, we give it should be it should be a distance between two successive crests or successive troughs at that point. So you take note of the two definitions that we give from there. But if it's an open question, even though you give two of them, any of them, you're right, we mark all of them. Then we look at oscillation or the cycle. Now oscillation or a cycle, remember something is moving in a circular, in a cyclic way. Like you look at the oscillations, the way oscillations move. Like in paper one, you looked at, you did practicals concerning oscillation, which means oscillation is the particle first moves in front, then it comes down, then that one becomes a complete oscillation. That's why I say that it's a complete to and from movement of a particle in a medium. So for something to have, should have a complete to and from movement of a wave particle in a medium at that point. That's the definition we give at that point. Then we have the period where the period, we normally calculate the period where we have small t and the n. So the period is the time taken for one particle to undergo one complete oscillation. So if a particle, that time the particle takes to undergo one complete oscillation is what we call the period. Someone can define it by saying a time taken for a wave particle, a time taken for a wave to travel a distance of one wavelength. So it can also be right if you put it in that form. We mark you also when you put it in that form. So you find that period is measured in seconds as usual. Then we have frequency. Frequency is a number of complete oscillation a wave particle makes in 1 second. When you find that when the number of oscillations that a wave particle makes in every 1 second is what we call the frequency, which means the frequency is 1 out of f, and it is a SI unit. As it is a SI unit is a Hertz, where if you're abbreviating it, we write capital H and Z. Then we have the phase. Now, when you talk about the phase, for the particles that are in a phase, you find that particles are in a phase, like for it, those particles that are on a phase, you find that they are exactly at the same point in their path or their movement, and you find that they are moving in the same direction. For example, when you come and look at this, just look at where period is. Now, if this line where we have drawn period is going through, when it's touching this peak, or we can use this one, when it's touching this peak and this peak, those are what you call those particles are in a phase that are in the same level. That's why we give it that the particles are in a phase are exactly at the same point in their path and are moving in the same direction. They will be going in the same direction, those particles. Then we have the wave front. A wave front, you find that any section through advancing wave in which all particles are in the phase, which means you find any section in that which is going through the advancing waves in which all particles are in the phase that are in the same level. That's what we call the wave front. I know you were being illustrated how it looks like in that thing when you're defining a wave front. Then we just have a ray, as you know, rays. In light, you did light. You saw how rays move light. You find that rays, that is the direction of the advancing wave. Where the wave is moving. That's what we call it. It is the direction of the advancing wave at that point. Then we have the speed of a wave, like we looked at the electromagnetic wave toward the speed of 3 exponent 8 meters per second. So which means the speed from the distance and the time, we say that is the linear distance followed by a wave per unit time. That is the speed of the wave that we give. So if you're being asked to define the speed of the wave, that is what you can go through the notes that you also have and look at it. So if you have any question, you feel free to ask, or you can raise up the hand. You can tell Mr. John to unmute and you ask, then we just be sharing now.
Okay, yes, friends, I had gone out, but you can ask some questions. Feel free to type in the chat, and I hope you can hear me. We can share. We can share together the questions that you raise. Before we go to the second part. Okay. Okay, so the second part is going to be questions on waves, the questions that we are going to try out on waves. Okay, friends, so I want to share a whiteboard. The rest is going to be a discussion. Questions? Yes, the answering techniques, questions, let us try them out. So, I want to share a whiteboard, then let me see. Good afternoon.
Auntie, we go the other side and you keep your money.
Where?
Christine,
My bag is here. I'm going to. I got a baby girl who's.
Auntie Joyce.
Okay. Let me see what to share.
So I'm going to babysit starting Friday.
Are you taking her the other side?
Yeah.
Hey, my house. You're taking her the other side?
Yeah. I don't know.
Whiteboard, I'm looking for the option for whiteboard.
No.
Oh, they are here, new whiteboard. Okay.
I was not.
I hope you can all see.
So when I say I'm going to babysit, you understand?
Are we able to see the whiteboard? I want to begin the discussion. Okay, thank you so much. So this is a second phase. Second phase is interaction, where we take you through the techniques of how to go about questions. But first and foremost, I want to appreciate Mr. Opio for that great work done. So he has taken us through the visual expressions and the picture of electromagnetic waves and the electromagnetic spectrum and so many other things. So I want us to have all the information that we've covered in some questions here. Yeah, in some question like someone requested. I request whoever is typing, please stop, because this is going to be very important equally for us. So whoever is typing, I don't know who has put something, but you can stop. Can stop. Okay, so the simple summary of waves, we said it is a disturbance of particles from their rest equilibrium position.
But I'm summarizing now.
This is my
Everyone is I know I have some online lesson I teach. So
okay. So if this is my rest position, this is the if I call it the rest position, from which particles are either displaced up or displaced downwards. So we said what makes a wave is that if we join the tips of these disturbances, if we join the tips, they form some kind of shape. Now that shape is what we call a wave. So it is the kind of shape that is formed as particles are being displaced from the equilibrium position. So the disturbance is in such a way that as a wave is propagating or progressing from one point to another, it carries energy with it. Is that okay? So you learned that the difference between two successive crests are these highest points. These semicircles are what you call the crests. So the distance between two successive crests, in other words, if you pick any two corresponding points, say for example, that highest point on the crest and that highest point on the crest, the distance between those 2 points is called the wavelength. Is that okay? But now, before I conclude entirely that that distance is wavelength, there is something I want us to look at. There's something I want us to look at very, very important. That something is, it all depends on what you plot against what. It all depends on what you plot against what. So if I have a graph of displacement in meters against distance, distance can also be in meters, centimeters, or millimeters. So, but the key point is that if I have displacement against meters, and then I have my graph, which is a sine curve, a sine wave. So this graph shall represent we say the graph represents the distance on the horizontal axis, where if I consider 2 points on my crest are these upper semicircles of the what? Of this wave. We don't call them circle, but cycle. So here we use the word cycle because it keeps repeating itself. A circle is simply drawn once. That is a circle. But where I have a semicircle, of course, a semicircle and a semicircle, they form a circle. But where this pattern is repeated again, then we don't call these ones circles. We call them cycles because a pattern keeps repeating itself. So that's the difference between a cycle and a circle. Is that okay, friends? So we are calling them cycles now. So if they are cycles, then we know that the difference, if we take the upper semicircle, then at any point along this cycle, the points, this one and also a point, okay, let me say point A and point B, the distance between the two is wavelength, provided the graph is displacement against distance, it becomes wavelength. Is that okay? On the other hand, if I changed the labeling to displacement against time, the same shape of the graph, but the distance between two successive crests, this time it is going to give me the period because I'm plotting displacement against time. So where I'm plotting displacement against distance, that the distance between two successive crests is the wavelength. Then here on the second part, the distance between two successive crests is the period because I'm plotting against time. Is that okay, friends? Are you following? Let me get one response before I got something else. Okay. Okay, that's okay. That's very good. So now we continue. So someone was asking for the answering tips. Tip number one, before you attempt such a question, be mindful of which axis, the labeling of each axis. For example, if it is displacement against distance, then you know that I'm dealing with wavelength. If it is displacement against time, then you know that the distance between two successive crests is the period. And like we said that they can be any 2 points. We already say successive. Now you got mark. Stop, you got mark. You got mark. Please don't disturb our work. You got? Okay. Kindly just if you want to say something, you can type in the chat. Speed against time. We don't have speed against the time. We don't have speed against the time in waves. It is displacement against the time or displacement against the distance. So if you want to get speed, we know that if you plot a graph of distance, when you plot a graph of displacement against the time, it gives the velocity or the speed. So, but when you plot speed against the time, that graph gives acceleration. So here we are dealing with the speed, which is displacement against the time. Is that okay? Or the wavelength, which is typically distance. Is that okay? Okay. So now let us have some questions bearing in mind what I plot against what. But before that, I want us to remind ourselves of the formula. Velocity is equal to F lambda. Velocity is equal to F lambda. I hope you derived that formula, but we shall just begin using it. So supposing we have a case where, I don't know if I'm using someone's screen or someone interrupted with my screen. It is not very sharp, but anyway, we can continue. So if I have a graph of displacement against time, time in seconds, you know that if I plot my graph, then the distance between two successive crests is going to be the period. It's going to be the what? It's going to be the period. And by the way, it can be any point so long as these 2 points are in phase. It can be a point somewhere here. It can be a point here and also another point here. That one is also, that distance is also period. Yes, it corresponds to the period. It can be a point between this and that. That is also period. Is that okay? Yeah, it can be a point between this and that, but we shall not make it more complicated. We shall simply say, we shall simply take the tips or the highest point of the crests or the lowest points of the troughs. So in that we mean, if I plot a graph of displacement against time, then between this highest point of the crest and this one, it's going to be the period, or between the lowest point of the lowest point on the trough and the lowest point on the trough, that is also going to be the period. So in that case, I can get the frequency. So this graph can guide me in getting frequency because I know period is 1/f. So if I know period, I can get frequency. That means that in a question where I have the velocity and the frequency, I can always get the wavelength. You see that? Is that okay? So for example, if our period is 4 seconds and the velocity is 16 meters per second, find the wavelength. Work out that one very fast. Find the wavelength. I'm waiting for the answers in the chat. Uh-huh. 64. Okay, very good. Very good. Others? So we're saying that if t is equal to 4 seconds and v is 16 meters per second, what is lambda? I guided you on how we simply use the formula v is equal to f lambda, but we don't know f, meaning that if you have the period 4 seconds, it can guide you. The period can guide you. Yeah? The period can guide you to get the frequency. Okay. If that one is fine, I think we can try out another number. We can try out another number. So this is distance in meters, and this is displacement in meters. So I have my wave. Let me say, of course, the maximum point is 1 and the minimum is -1, because this represents a sine wave. So if this is 0 and we call this is 6, and then this is 9, 12, 15, 18, 21, 24, and so on. So question number 1, can you work out the following? Calculate or find, and say, find the find the Roman 1 period. Yes, we can. Okay, we can find the period Roman 2 amplitude, amplitude, and let me give the speed of the wave. Let's say it is 4 meters per second. So period, amplitude, and the wavelength. Roman 3 is the wavelength. I think we can work out that. Period, amplitude, and wavelength. Is someone working out? Okay. Amplitude. Others. Others, yes. Okay. I think let me just pick someone to take us through. Who is willing to take us through? I give you opportunity. Yes. Okay. The name is, I've forgotten the name. Kutesa. Francis. Okay, let me see. Francis, where here? Okay, Francis, you can start and share with us. Unmute. Francis, unmute. Uh-huh. Okay. Someone is saying that we want a wave theory of light. It will come, don't worry. Don't worry, let us just... Hmm? Hmm. Yes? Anyone willing to take us through? Okay, Yiga. Yiga, please do. When is the facilitation of wave 2? Let us first get wave 1 on our fingertips. Okay, you gotta take us through. Yes? Okay, seems we are running short of time, but we know that if it is plotted as displacement against distance, then the distance between two successive crests is called the wavelength. So I know the wavelength and I know the velocity. If I'm using v is equal to f lambda, where I know the velocity, I know the wavelength, I can get the frequency. And I know period is 1 over f. So if I know frequency, then I can get period. Is that okay? Of course, wavelength is between two successive crests, which is 15 minus 3, you get 12. So that is it, I think. The amplitude is the maximum displacement of a wave from its resting position. Is that okay? Okay, now let us look at some more calculations and applications. Okay. That is the progressive wave equation. The progressive wave equation. So we shall look at the progressive wave equation and then we shall stop there for today. So next time we shall build on that. So the progressive wave equation, let me just discuss it. We shall look at it. We shall look at it another time. Is that okay? So the type of this equation or the type of graph that we have here is for those who have ever plotted a sine curve or a sine wave. So when you plot a graph of, let me say, for instance, where you plot a graph of y is equal to sine theta. In trigonometry, I think you must have learned this. When you plot a graph of sine theta against theta, what do you come up with? A graph of sine theta against theta is a sine what? Is a sine curve, not so? So likewise, a wave energy of the wave. Okay, let me first look at this one. We are going to look at the energy of the wave if time allows. And so we are saying that when we plot sine theta against theta, what we come up with is a graph of this nature. I think I can make it better. Is a graph of, we don't have time, we would have gone into details of plotting. That is, if we plot sine theta against theta in degrees. So for the highest point of sine theta is a 1 and the lowest is a -1. For values of theta equals 0, here there is 180 is pi, and then we have 2 pi, which corresponds to 360, and also 3 pi, and so on. Is that okay? So in such a graph, when you plot sine theta against theta, this is what you come up with. So we know that when you plot a wave, most especially a progressive wave, we come up with a graph that is the same as this graph. Therefore, we can simply see that sine or the graph represented by a wave displacement against distance is also sinusoidal, because it can be represented as a sine wave in a way. Is that okay? So if a graph of the wave can be represented in this nature, that means that if we are to relate with a general wave graph, which is also characterized by displacement okay. Displacement against time. This one is becoming insensitive. Okay, so the other side was displacement. So if we are to relate with a sine wave, the equation for such a graph will be, if instead of displacement I simply call it what? If instead of displacement I simply call it y. I simply call it y, but of course in meters. Then the other side I have time. So the graph is going to be y is equal to a sine theta. Now the theta in this case is called the angular displacement. Angular displacement, but of course here we consider the A as the maximum displacement. Remember, if it was a sine wave, if it was a typical sine wave, a sine curve, A is always 1, either 1 or -1. But here, A might be anything else. It might not be necessarily 1 because we are dealing a wave graph. So A can be any value, not necessarily 1, unless if we are dealing with a typical sine wave where the maximum displacement is either a +1 or a -1. So the general equation for this wave is y is equal to the amplitude sine theta, where now this theta in this case represents the angular displacement. And from circular motion you learned, angular displacement is given as, who remembers the definition of angular displacement? Yes. Angular displacement is angular velocity times time. You remember? Angular velocity times time. Therefore, our formula can be y equals, our formula becomes y equals the amplitude of the wave, which is the maximum displacement from the rest position, then the sine times the theta. Theta is our angular displacement, which is the same as the angular velocity times what? Times time. Is that okay? So we take note that this is the basic. When I say basic, that is the beginning formula, of waves. As we progress from the simple ones, the simple applications that we had, now we advance to application of trigonometry or application of sine, application of trigonometry as far as waves are concerned. Is that okay? Any questions so far? Yes? Okay, so let us look at something. Everything is clear, very good. Let us look at something that is also very important, and that is the phase difference. The phase difference. I say if we have, if I have my wave as this one, sir, I see we are running out of time, but I feel like we should also touch resonance. Please don't take us so fast. We shall reach resonance, don't worry. We still have some few meetings. We shall reach resonance. So we need the introduction. So I'm saying that for cases where we have a wave like this one, y against time in seconds, let's say y in meters, y is simply displacement against time in meters. So let's say that we have 2 points. There is a point at A, and then there is a point at B. The point at A and the point, let me represent the point at B somewhere. So let me represent a point at B like that. Because I told you that what makes this kind of wave is the displacement of the particles. So it means that particles are displaced at some distances from the equilibrium position. So we can have cases where all particles are along the equilibrium position. All particles are along the equilibrium position. And also we have cases where a particle is along the equilibrium position like a particle A, but B is displaced from the equilibrium from the equilibrium position. Is that okay? So if I trace the point of B along the rest position, then the distance from point A, which is the origin, that distance, I can call it X. That is not wavelength. I can simply call that point, that distance what? That distance X. So we say that there is a phase difference between the particle at point A, which is the origin, and point B. And that phase difference can be represented as a relationship between the wavelength and the distance from the origin. So the phase angle in that case is given as 2 pi. We said it is a relationship between the distance from the origin and wavelength, because we know that 2 pi is a constant. So the phase angle relates the distance from the origin to where another particle is, for as long as that particle is not exactly along the same equilibrium position with the previous particle, and also for as long as we don't have these two particles having the difference as the difference of the wavelength. I think this I need to re-explain it. Someone might be lost. Okay, let me repeat. I have a particle at point A and a particle at point B. So the particle at point B, if we draw a vertical line to trace its position along the rest position, it would be somewhere. Let me call this point Q. Now, the particle at point B is both at a certain angle from point A. In other words, the difference is in two types. The difference in angle, because remember, this wave as it progresses, we call it a cycle. That for a cycle if I'm just to sketch it like this, every time a particle moves, an angle changes. If a particle goes to another position, an angle changes. Moves to another direction, an angle changes. But remember, it's not a circle. A cycle is where the angles change, but following a particular pattern, not following just a circle like that. A circle is simply a representation of what happens to show you that every time a particle moves, there is difference in the angle from one particle, and also difference in the distance from that very particle. So the difference in the angle, we call it the phase angle. And then we also have the difference that corresponds to the distance between the 2 points. So if we consider the phase angle, then it relates with the distance from one particle in the formula given as that. Is that okay? So here we say that one particle is leading the other by a value which is equal to this formula. Meaning that if you have x, the value for x, and you know the wavelength of this wave, you can know by how much or by what angle this particle leads the other. I don't know, am I understood? Maybe I need to get a comment to read, to check in the comments. I see we are running out of time. Okay, this is a previous comment. I don't know, someone said something, because I don't want us to wind up. I wanted us to look at this phase angle, and we stop at that for now because of time. Can I have just a comment? Okay, I just pardon. Okay, so we are saying that supposing we have point A. This point A is exactly at the origin. The origin is the point. Okay, the origin is the point 0, 0. Then there is point B. Point B still along the wave. But now when you look at this point B, if you are to have it as a circle, point B, if you are to have it as a circle, and this is your point A, this is point B, there is a difference. There is a difference between point A and point B in terms of the angle. In terms of the angle. That is one. Number two, because we are not considering a circle, we are considering a cycle. Remember, a cycle deals with a pattern that is repeated. So meaning that it is point B is not only different from point A by a certain difference in angle, but also it is different from point A by a certain distance. By a certain distance along the horizontal line, or the equilibrium position. So we get the what we call the phase angle. We get the phase angle, which is now in simple terms the difference when you consider only the angle difference between the one point and another. So that phase angle relates the distance from one point and the wavelength, and the formula is what we have here. The formula is what we have here. Now, what is the importance of the phase angle? The phase angle guides us in finding by how much one particle is either behind the other, we call that one lagging, or the difference through how much, or the difference by how much one particle is ahead of the other. That is, we call it leading. So a particle can either be leading the other one or lagging. Of course, if one particle is leading the other, automatically the other one is lagging. So that calculation and the relationship is what we call, is what we derive from the phase angle. So this expression I have written guides us in finding out by how much degrees is this angle. Someone asked for the units of phase angle, degrees, or they can be radians. Okay, we don't have time now for deriving it, but I think you just need to know it. You just need to know this one. No one is going to ask you to derive it, but there is a very simple derivation. For now, allow me to wind up. So the phase angle relates the distance between one point and another and the wavelength. And I've told you it guides us in finding by how many degrees one particle is ahead of the other, or by how many degrees one particle is behind the other. That is the phase angle. So that means that if we are to go to our formula, which is y equals the amplitude sine omega t. Is that okay? So y is going to be a sine omega t, either plus or minus that angle. Now, here I'm relating a wave where one particle is Okay, let us wind up.
That's it.
Yes. Thank you so much.
Thank you, too.
Safe journey. Okay, let us wind up, because I wanted to relate the two, but someone, let us wind up,
This is for Reverend.
Just 3 minutes, yeah. Okay, so okay, let me wind up this one. We saw that where you have y is equal to amplitude sine omega t, we looked at that one. Then if we are considering a particle along the sine wave, this is the origin and our particle is somewhere here. Our particle P is somewhere there. Then we say that this particle is not only at a certain distance x from the origin, but also it is a certain phase angle. I don't want to draw it like this. It's supposed to be drawn in 3D to come out well, but you just know that there is a certain angle between this particle P and any particle that is at the origin, like I explained. So as I wind up this one, I'll say that the relationship between x and the wavelength we said is simply, it can be from the origin to this point. So that relationship between x is called the phase difference. Then phi or phi is called the phase angle. So the phase angle relates the phase difference, which is x, by a relationship, that one. Now we say that the particle P is ahead of a particle at O by a phase difference, that one. Is that okay? So to write this one mathematically, we simply say y equals a sine into omega t, then plus that phi, where the phi I can write it as what? The phi I can write it as 2 pi x over lambda. So this is a formula I wanted us to have on our fingertips. The second part represents the phase angle, which can be written as 2 pi x over lambda. So if we are to meet again, this is the exact point I want us to look at. That is, someone was so much interested in energy, but before we look at energy, we need to build something. So please take note, remind me anytime that as we meet, we begin with this very formula. It is a very important formula in waves. Any question? Yes? Okay, I think we can stop here for now. I hope you have picked something. Have a blessed day.